Potential of generating renewable energy using Picohydro Turbine from wastewater. Abstract: fossil fuels depletion, climate change, global warming, and energy insecurity are driving factor, which has posed serious concerns over conventional energy sources. To mitigate and slow down these issues, the world is moving toward clean and renewable energy sources, RES. Amidst all RES, hydro is the most mature technology. Picohydro installed over sewage pipelines and water supply pipelines, which is free from these concerns. Picohydro turbines have great potential to electrify the rural and hilly areas. In this project, a Picohydro turbine was designed which has installed on sewage pipelines to produce electricity. The project has 3 phases. In the first phase, sewage pipeline water quality has tested in a lab in terms of pH, dissolved solids, and suspended particles. As suspended particle and acidity of the water can result in failure and corrosion of turbine. The theoretical power and energy available in the sewage pipeline was calculated. If these 2 phases of testing enhance the feasibility of the project, then the CAD model of the turbine has been made using SolidWorks. Then lastly, the turbine has been manufactured and installed. This project used the flow of sewage water to produce electricity and help to reduce energy security, GHG emission, and global warming. Keywords: fossil fuels depletion, climate change, renewable energy sources, RES, Picohydro turbine, sewage pipeline, CAD mode, GHG emission. Introduction. Sustainable energy is being explored rapidly day by as fossil fuels are depleting and their cost is increasing due to energy insecurity as well as their negative environmental impacts. 1. Renewable energy has got great potential to meet the global energy demand and to overcome global warming and climate change issues. The state-of-the-art known renewable energies are hydro, wind, solar, and hydrogen energy. Amidst all these renewable energy sources, the potential and efficiency of hydro energy cannot be underestimated for future power generation in terms of sustainability as well as environmental friendly behavior too. As hydro energy is naturally available globally and produces no GHG emissions and other harmful emissions. 3. Of course, in terms of aquatic life, hydro energy poses a greater threat to aquatic life resulting in their killing and migration. But advancements in hydro energy technology in the form of gravitational water vortex system and other technologies have provided solutions regarding this issue. 3. Owing to be most ancient and matured energy technology among renewable energies, hydro energy is the most explored, secured, efficient, and reliable form of energy. 4. The statistical data of the world energy mix shows that hydro energy makes 20% of the global energy mix. 7. Using the natural tendency of water to flow from higher potential to lower potential, the potential energy of water is utilized to rotate the blades of turbines. The conversion efficiency of hydro from water to wire operation has been reported to be almost 90%. The capital cost of hydro schemes is relatively higher, but they require very low maintenance, which makes them more reliable and efficient. 5. Water flows from higher potential to lower potential, thus, the potential energy gradually decreases and kinetic energy of water increases. This kinetic energy helps to rotate the blades of turbine and get converted into mechanical energy of the turbine. Now mechanical energy of turbine is converted into electrical energy by coupling the turbine with generator through Excel. The working principle of hydro energy has been shown in Fig.1. The power produced depends upon the water head, storage capacity, and efficiency of the turbine and generator. Recent researches have been made on the exploration of simple hydro turbine designs to reduce the capital cost factor. 5. Hydropower is a vital source of energy for hilly and rural areas, thus imposing less load on the central grid. 6. There are different kinds of turbines. They are: A. Impulse turbines. For low to high heads ranging between 6 feet to 600 feet, impulse turbines are preferred. 7. The kinetic energy of water in jet form rotates the runners of the impulse turbine to produce electricity. Water enters from the top side of the turbine and leaves at the bottom side with pressure equivalent to atmospheric pressure. 7. Impulse turbines are inexpensive due to their simple design. Impulse turbines are further categorized into following turbines which are suitable to be installed at low head: A. Turgo, Pelton, and cross flow. B. Turgo turbines. Fig.2 shown the design of a turgo turbine which was made by Gilbert Blythe back in 1927. These turbines find their application in medium to the high head range. 6. These turbines are efficient for higher flow rates and low head application as they outperform in power generation using more water and less head. 9. 10. Water jet strikes the runner and leaves it at bottom of the runner at a sharp angle, thus presenting no interference to the inlet jet. 4. This feature of the turbine enables to have high rotational speed with a low diameter. 9. 10. This phenomenon has been explained in Fig.39. A picture containing metalware, gear. Description automatically generated. See Pelton turbines. Pelton turbine has been shown in Fig.4, in which it can be seen that how water strikes the cupped buckets of the turbine with the help of nozzles. These cupped buckets are arranged on the periphery of the turbine and help in turbine rotation. These turbines possess a higher efficiency rate ranging between 70 to 90%. 11. The number of nozzles for the Pelton wheel turbine can be one or more than one depending upon the application. At sites having higher flow rate as well as higher head, similarly the sites having low flow rate as well as low head, impulse turbines are better choices in both cases. 7. For small-scale applications, single nozzle water jet is preferred. 9-10. A picture containing diagram. Description automatically generated. Fig.4 Pelton wheel for small hydro projects. D cross-flow turbines. These turbines were designed by Ausberger Co., that why they are called Ausberger turbines. These turbines are drum-shaped having cylindrical-shaped runners. The cylindrical-shaped runner is equipped with curved vanes against which the rectangular section nozzles are directed. Cross-flow turbines have the advantage that water flows twice through its blade. In the first cycle flow is direct from outside to inside, while in the second cycle, water flows from inside to back out. The design of cross-flow turbines has been shown in Fig.5. Diagram. Description automatically generated with medium confidence. Fig.5 Inflow in horizontal and vertical orientations. Propeller turbines. The reaction turbines which are in operation so far are mostly propeller type owing to their simple design, efficiency, and cost effectiveness. 13. Figure 1.6 shows the design of the propeller turbine having 6 blades on its runner. The striking rate of water on these blades is constant irrespective of their blade pitch, which either is fixed or made adjustable. 13. Furthermore, turbine consists of 3 more major components which are termed as scroll case, draft tube, and wicket gates. 14. Further classification of propeller turbines goes into bulb turbine, unity cased generator installed on front of water flow, stir flow, generator directly attached to turbine circumference, tube turbine, penstock and generator connection is a straight line. 14-15. The Kaplan turbines are in fact the propeller turbines and have variable pitch. These turbines were first designed by Kaplan in 1913, thus has been named after its inventor. The only difference is that its hub is provided with a mechanism to adjust the blade's angle as well as the wicket gates. Figure 1.7 explains this phenomenon. 12-15. Fig.6 The bulb propeller turbine. 2. Problem statement. Mostly the remote areas are deprived of electricity, which is basic need of any society. This may be the case even in those countries which have extensive transmission and grid network. The demand of electrification in remote areas is of high concern. Despite of these concerns, most of areas are not electrified as power consumption rate in these areas is low and will put an enormous cost on transmission lines. Furthermore, the prices of other daily usable goods are also high in these areas. So, it demands for an on-site power generation technology which may full of their energy needs. Picohydro turbines are best solution to this problem, as they can be installed on water supply pipelines, sewage water pipelines, or any nearby waterfall and canals. The sole purpose of this project is to work on prototype of Picohydro turbine which will enable the electrification of remote areas and isolated communities. A prototype of Picohydro will be made to study the current scenario of Picohydro electricity production for rural and hilly area, electricity production for on-site application, and the results obtained from this prototype will form a basis for large-scale application of Picohydro. 3. Literature review. A Picohydro overview. The Pico term in hydro technology stands for hydropower generating systems ranging between few watts to 5 kilowatts. 20. These systems are best suited for rural and hilly areas electrification with cost effectiveness. 21. The increasing inflation rates, as well as electricity bills, have urged people to find ways to maintain the standards of their lifestyles by producing electricity for their own. The sole purpose of Picohydro is to serve the rural areas' electrification needs. But these days this technology is made in use to generate electricity by regulating the water flow in domestic areas. The prototype of Pico turbines is designed to be installed at water supply pipelines and to produce electricity. These pipelines contain a huge potential to generate electricity, but so far, this potential has not been explored and power generation from these Picohydro systems is limited. 22. The potential of Picohydro is not the same for all areas, as the pressure of these water supply pipelines is different in the different areas, thus potential will also be different. Also, the hydropower depends upon the water flow rate too, so the potential will also depend upon the water flow rate in these water supply pipelines. Therefore, Prior to the installation of the Picohydro turbine, the head of water and water flow rate must be considered. These Picohydro systems not only will reduce the load on the central grid but also help to reduce the threats posed by GHG emissions in form of climate change and global warming. 20. Also, the dependency on fossil fuels will be reduced, resulting in a secure and reliable energy supply. As these hydro systems require no reservoirs, so the other advantages couples with Picohydro are no deforestation, no threat to aquatic life, no soil erosion, and migration of local people. 23. Picohydro are a type of run-of-the-river in term of technology classification, as they use the flow of water and put back into pipeline. 24. B. Background. Joel Titus et al. Designed a Pico turbine on sewage water pipeline. The impulse turbine design was such that it did not cause any loss in mass flow rate. The installation of turbine was done on the overhead tank outlet. The conversion of kinetic energy into electrical energy was done by using this turbine. The head of an overhead tank was 14 m and discharge was 9 L/s. It was observed that at an average flow rate of 8 L/s, the maximum power produced by this turbine was 212 watts. 25 mjm Riesdoen et al. Work came out with the description of initial testing on Picohydro prototype. This prototype was installed on domestic pipeline supplies which were using water kinetic energy to produce electricity without disrupting the water supply that is being used for cooking, laundry, and bath. The results of this prototype showed that some values of voltage were recorded from the generator, which implies that Picohydro is feasible for domestic electrification and can be further improved for large-scale application. 26. Sujith Kumar et al. Reported a study on Picohydro economical models near green buildings. As Picohydro is free of cost energy and cheaper than all other renewable energy sources, they reported that a Picohydro can be integrated into any building, and this system is capable of producing 100W to 500W, which can illuminate 5 to 6 LED bulbs. 27. OJMO et al. Designed a Picohydro prototype to harness the energy contained in falling water. The turbine used had a runner with a single jet and bucket geometry, was hemispherical, having 50 mm diameter. The hydraulic head was 3.4 meters and the reservoir capacity was 2,000 gallons. Results showed that this prototype was able to produce 4.5 W of electricity with turbine revolutions of 500 rev/min. They reported that the power generation could be enhanced if the system can be upgraded to a scale of 110 for the diameter of a runner, head, and capacity of the reservoir with a step-up transformer. 28. IW Ratana et al. Developed a hybrid power plant, HPP, which consisted of solar PV and Picohydro. HPP capacity was enhanced to 500-1000 W in the second stage, while it was 100-200 W in the first stage. In the first stage, Picohydro was producing 86 W out of 100 W, while PV was producing 30 W on a sunny day out of 100 W. The output of Picohydro was in AC, which was converted to DC and combined with the DC output of solar PV. This DC current was stored in one 2V DC battery. The capacity of battery was 2-3 A current, which was enough to light a few LEDs. 29. 4 Concepts and design. There are many impurities carried by sewage water that may include hair, human waste, bathroom, and washroom waste as well. This requires the hydro turbine, which may not be affected by the presence of these impurities. Because if these impurities cause blockage in turbine, this will affect the overall performance of turbine. Therefore, the Pico turbines having hollow circle around its central axis will be used in this project so that impurities may pass through this hollow structure and may not cause the turbine blockage, which will affect the turbine performance. Fig.7. Shown below is design of hollow Picohydro turbine which was installed at Toyagawa River Basin Sewerage, Japan. 4. The area of pipe covered by the sewage flow was 10%, so the power produced was 328 W. The efficiency sum of hydraulic efficiency, electrical and turbine was found to be 0.2 P for this turbine. We will use same turbine design in our project with some adequate modification. A circular pipe is inserted between two stationary pipes, with their axes on a line. The inserted pipe is supported by two bearings, thus, the pipe can rotate around the central axis. A runner is embedded within the inserted, rotational, pipe. When water flows in the pipe, the runner and the pipe rotate integrally around the axis. A guide van is mounted at the end of the stationary pipe, just upstream of the rotational pipe. Fig.8. Shown below explains the runner. It has 4 blades, and a circular hollow is provided around the rotating, central, axis so that foreign matter included in the water can pass through the runner. The ratio of the hollow diameter D2 to the pipe diameter D1. It is defined as the hollow ratio E equals D2/D1 equals 0.375. The runner is composed of a flat plate cascade. The Fig. 9. Shown below is 2D development view of blade. The width and thickness depends entirely upon the sewage pipeline diameter upon which turbine is going to be installed. This study will implement this design to perform experiment for power generation from Picohydro Turbine on sewage water pipeline. The specification of runner and turbine parameters can be changed to enhance the performance. The Fig. 10. Given below shows the hollow structure of guide vane provided around the central axis. This hollow structure will prevent the turbine to be blocked by impurities present in the sewage water. Thus, there will be no need to use water filters in this Picohydro turbine. V. Methodology and implementation. The overall project implementation and completion is divided into two phases. A. First phase. For the first phase, the inception and conceptual stage takes place. Within this phase, several researches will be reviewed which deemed appropriate for the project as well as identifying the problem statement for current objectives. Afterwards, measurement and data gathering will be starting at the control site, and this may include the dimension of the water channel, m, flow rate, m3/s, and also velocity of water, m/s. From hand sketches to using SolidWorks CAD software, the overall design of the components for the system, Picohydro Turbine, are modeled in 3D. B. Second phase. This phase involves the implementation and analysis stage. The fabrication will involves connecting developed 3D printed Picohydro turbine with an DC generator. After fabrication, site testing will proceed with the produced system model. Several measurements will be taken on site such as power output from the turbine, W, torque produced, RPM, as well as velocity of water flow and jet flow, m/s, which are important to study the effect of these parameters on turbine performance. Afterwards, a feasibility study for implementing system for the generation of electricity from waste from industrial environment will be carried out. The Fig. 12. Below shows the flow chart of the overall implementation. The project have been designed on the SolidWorks software installed on the PC. The individual of the project will be discussed with specified dimensions as per the requirement. Runner blade. This is the main component of the turbine that route the body in order to generate electricity. Water guides. This part guide water to hit the blade of the runner directly. This part holds the bearing in order to enable the turbine to rotate the generator. 6. Simulation results. The sewage water current in the pipeline hits the turbine with pressure as the magnitude of this pressure decreases or increases depending on the location of this turbine within the pipeline. The hollow turbine design makes it easier for the solid impurities present in the sewage water to pass through the turbines begin to rotate under the influence of the flowing stream of high pressure water. When the turbine is in motion, the motion is transmitted through the rubber belt to rotate the generator. When the generator is rotating, it produces electricity, which in turn feeds the local network with electricity, or it may be used to supply electricity to remote areas that cannot get it from the network. 7. Results and analysis. We made our experiments to study the hollow Pico turbine electric outputs and to know how this design system can deal with the different types of water. As it can be seen from the above analysis, with increasing contamination, flow rate of water in water channel starts decreasing, which reduces the turbine efficiency as well as the power output. The highest efficiency of turbine is obtained with tap water, which is free of contamination, while lowest efficiency was obtained with drainage water having high contamination. This is due to low flow rate at high contamination. Low flow rate produces less power, thus reduces turbine efficiency. As all industries produce waste which is channelized through sewage pipes. The installation of Picohydro turbines on these sewage pipes can produce electricity which will enable the industry to power the lights and other small power electrical devices. This will reduce the power consumption of industry, reducing their electricity bill too. Less electricity bills mean the overall profit of industry will increase. Thus, Picohydro turbines can help industry to increase their revenue. Also, it is renewable energy source, so it will earn carbon credits for that industry. 8. Recommendation and future works. As far as future work and recommendations are concerned, mechanical power transmission of Picohydro should be studied in detail. Smooth and with less friction operation of the turbine must be ensured. To ensure that the design is reliable for future energy production, a detailed study must be conducted on the dynamics and kinetics of design. To harness more energy, the turbine efficiency is a key factor. The efficiency of the turbine can be enhanced by working on the design, shape, and manufacturing process of the turbine. Due to stress concentrations, right between the blades and base plate, the crack may be initiated, thus design needs to be improved in this sense too. More research studies need to be conducted to overcome the challenges faced in efficiency of Pico turbines and its commercialization. Future of Picohydro not only lies in technical development but also it need developments in economics and policy. Unlike rest of conventional energy sources, Picohydro is green and clean source of energy which will contribute toward reduction in GHG, global warming and climate change. Picohydro installation in remote areas will not only help to electrify that area but also will create jobs for local community. Government should contribute toward friendly policy for Picohydro to remove barriers and encourage investment from private sector. To get maximum out of Picohydro projects, site visit and survey must be conducted to take in account the head and flow rate so that expected power outcome may be calculated. These surveys will help to make Picohydro projects more economical. Continuous inspection of Picohydro must be conducted and maintenance like greasing/lubrication of bearings must be brought into business to enhance the lifetime of project and reduce the power losses as well. There are many key points that ensures the bright future of Picohydro. Few of them include high grid cost in remote areas, low head sites are ideal for Picohydro, improved living standard of remote areas community and green energy conversion technology etc. 9. Conclusion. Picohydro turbines have great potential to electrify the rural and hilly areas. This paper was aimed to design a Picohydro turbine which was installed on sewage pipelines to produce electricity for local population. The project was divided into 3 phases. In first phase sewage pipeline water quality was be tested in lab in term of pH, dissolved solids, and suspended particle. As suspended particle and acidity of water could result in failure and corrosion of turbine. The theoretical power and energy available in sewage pipeline was be calculated. These results of first 2 stage phases were satisfactory, thus taking into account the feasibility of project, the CAD design of turbine was developed using the SolidWorks software. The turbine model then was manufactured and installed on sewage water pipeline. Picohydro a promising technology of the current scenario and future in terms of power generation and overcoming climate change issues. This technology without loss of mass flow rate in pipeline generates electricity. This technology only uses the kinetic energy of water. The designed project depicts that Picohydro turbine installation in all the nations can help to reduce the load on the central grid as well as to mitigate the GHG emissions.